Okay, Alex, looking forward to hearing from you. Thanks.
Thank you so much for the invitation and for this wonderful seminar series that I'm really excited to that it continues this year. So this talk is on computational Lebesgue integration, and let me start with the good news, which is that you do not need measure theory to understand this talk. So the reason I'm using the terminology Lebesgue integration here is simply from the fact of what is the API of that type of integral. So remember that for the Riemann integral, we assume that the input space of the function we integrate is Rd. And whereas for the Lebesgue integral, the only thing we assume is that the output is the real. We don't make a very strong assumption on the input space. So that's the reason for this terminology. So let me start a little bit with some motivation for why this topic is, I think, interesting and important. And I'll start back to basically the basics of statistics. So how do we measure, quantify uncertainty? So the field of statistics started largely with classical methods, where we assume that we're estimating a vector. And this is a substrate for normal approximations. So that works in many contexts. But there are many things that are not vectors. So I show some example here. So there are networks, there are trees, molecules. And moreover, if they are coerced into vectors, they do not necessarily exhibit asymptotic normality. So these classical tools, they do have this important limitation. And in my opinion, that's my first reason why I like to use Bayesian methods, is that they allow us to do calibrated uncertainty beyond vectors. All right. So what I think should be called the fundamental theorem of Bayesian statistics is this very simple fact that is a one-liner proof that Bayesian credible sets over arbitrary space are calibrated when the model is well specified. And the important word in this talk is arbitrary. So it can be a space of trees, for example, and we can still, a tree that we could try to reconstruct, and we can still formulate the problem of quantifying uncertainty with that input space, the space of trees. So just to flesh out this example a bit more, so this is something that most of my applied stat work is concerned with. So I'm just going to do a quick sketch. So the task in Bayesian phylogenetic inference is to reconstruct the ancestral relationships, so the phylogenetic tree, based on some data. Often the data has the form of a matrix where on one axis we have the genomic positions, and the other axis is several organisms. So it could be different animals. In my case, it's often different individual cells in a cancer tumor. But the key idea is that from that data, we try to reconstruct not only one tree, but the uncertainty over that reconstruction, keeping in mind that some part of that reconstruction will inherently always be uncertain because we have limited data. The past is lost forever. And the way this is done in a Bayesian context is on the left, that's what we seek. So some uncertainty over tree reconstruction. So that's a whole topic, how to encode this. I'm not going to go over that in details, but there are methods. This is a nice visualization here that shows kind of a cloud of trees. And to achieve this, we have an MCMC algorithm over the space of phylogenetic trees. So this is a kind of a visualization of what I will call the state space script X, where each point X is a tree in this example. And we're going to try to compute integral over that space, essentially. All right. So this is the motivation. So hopefully there's many of you that have other things in your applied statistics work where you can connect with this general setup. So let's talk a little bit about the computational methods to perform that task. So I'm going to use the following notation. So I'm going to denote pi naught to be a reference probability distribution. So some of the things in this talk could apply beyond Bayesian statistics, and it does. But to keep things concrete, I will use the Bayesian language. So pi naught will be, you can think about as a prior distribution. Script L would be the log likelihood. Pi will be the probability distribution of interest, so posterior distribution. And so by Bayes' theorem, we can rewrite, we can express this posterior by the likelihood times the prior divided by a normalization constant, which is the integral of the top. And that's, for example, in the Bayesian context, would be the evidence or the marginal likelihood of the data. So this gives you a sketch. So we have this positive function on the top, and what we seek to compute is the area under the curve, but where X is at this abstract space, the space of trees, for example. So in Monte Carlo methods, there's kind of two big tasks that people are interested in. So one is expectation with respect to pi. Another one is the normalization constant z. I'm going to focus on two. These are closely related one to each other. You can do one with two, for example, but I will focus on two to clean up the discussion a little bit. So just to reinforce the notation, and give an example of concretely why do we want in phylogenetics the normalization constant. Let's say that we want to do model selection in Bayesian phylogenetics. We have two evolutionary models. So script X, as I mentioned, is the space of phylogenies. Small x is one phylogenetic tree, and Z will be the evidence of our evolutionary model. And so by comparing this number for two different models, we might come to a conclusion on which one this data supports. So this x-axis corresponds to that cloud of points. So I'm still going to denote it with an x-axis. That's the real, but that's just a cartoon. Keep in mind that the x-axis is unstructured in this talk. And the question that this talk is about is methods to approximate Z, this area under the curve, when script X is not the Euclidean space Rn. So in order to tackle this, we need sort of two bodies of literature. So one of it is domain specific. So we need people that study MCMC on trees, on networks, and this will always be needed. What is interesting, though, is that there are some generic tools that apply to all of these different problems. They do this talk will be about this second point. So generic tools that always apply when the Lebesgue integral is defined. But I want to emphasize that it doesn't take over the first point. They assume that the work has already been done by domain expert in specific state space. For example, if you're interested in phylogenetic move using Bayesian statistics, you can see that nice paper, Lackner et al. 2008. There's all sorts of different moves that are needed to explore the space of trees. But surprisingly, even in the very generic setup of Lebesgue integral, there are a few things that we can say, which is maybe a bit interesting in the computational front, I think. So the only thing that we're going to review from measure theory is essentially Lebesgue's big insight that if we have a generic integration problem, the x-axis is a black box. It's just a measurable space. But in contrast, the y-axis is always the real. Otherwise, the Lebesgue integral is not defined. We need to be able to add things and multiply. And so the Lebesgue integral in the theoretic side leverage the known structure on the y-axis to define integrals. Okay? That construction is not computable. It's not going to be useful. But the general insight of leveraging the y-axis, I think, is something we should think about when we think about computation. Now, this setup, I want to reinforce this message, is too broad to have algorithms. I'm not going to give you a full description of how to compute Lebesgue integral. What we're going to get is meta-algorithms. So algorithms that take as input an algorithm and augment it, in a sense. Okay? Now, maybe the most interesting generic tool that applies to all Lebesgue integration problem is a notion of, or actually several notions of interpolation. So instead of just considering this pi1, the posterior, where the normalization constant is difficult, I'm going to interpolate with another endpoint being an easy distribution which in Bayesian statistics is almost always available, is the prior. So I'm going to assume that the prior I can normalize, so I can write Z0 in closed form, and I can sample IID from it. Okay, so that's often the case. And we're going to consider interpolation between the two, which the most common example is called annealing, where we take the log likelihood, multiply it by some value before exponentiating it. Okay, so this will change the normalization constant. So we now have like also a sequence of normal or continuum of normalization constants. So in this talk, a couple of times I'll do this Lebesgue compatibility check where I ask, okay, I just talked about a concept. Is it compatible with any Lebesgue integral? And here we can see that this is the true. So this is true. The log likelihood, even if it takes a tree, it outputs a number, so I can multiply by a number. So that's okay. And interestingly, the first example of this idea, or one of the first examples by Geyer and Thomson in '93, was precisely for a combinatorial space, so the space of pedigrees. So this idea has been around. I'm just reinforcing it a little bit here in this talk and reviewing it. So now that we have a continuum of distribution, algorithms will typically need a discrete sequence. So there will be an important step called the discretization of this schedule. So this is going to give rise to these beta 1 up to beta t, where big T is going to be the number of discretization points. Okay, and so you can see that this informally will morph the density from maybe a unimodal prior into potentially multimodal posterior. So why do we do this? This is an old trick, but a very important one, that we're going to break the ratio of Z1 to Z0 as a product of telescoping terms. And if it's done right, this can lead to a reduction from exponential time complexity to polynomial complexity. So it's one of the rare cases that really we can, in some situation, beat the curse of dimensionality. Although, as we'll see, the notion of dimensionality will not be defined in our case, but we'll replace it by something similar. So now I can finally, based on this notation that I've given you, introduce this notion of a black box Lebesgue integration problem. So what do I mean by this? It's a problem where you're given as input a Bayes MCMC algorithm that targets pi beta. So I give you one of these intermediate distribution. You can give me k sub beta that targets that law. I'm going to call these explorers. And also I can evaluate the log likelihood, which in a more sort of general framework would be the logarithm of the random derivative between the two endpoints of that annealing sequence, up to a constant, okay? And the goal is to compute z hat, an approximation of the normalization constant z, which was that integral under the curve. Just to kind of first, a little preview that this is not vaporware, that there's some actual algorithmic contents. We've been developing a software package that it works in many sort of degrees of generality, but one of the degrees of generality, one of the API is exactly what I described, okay? So here's the situation where this software can be useful. Let's say that you wrote some MCMC code in any programming language, okay? So you just have this black box MCMC code, and you can accept a beta. So you can target a different annealing sequence. Let's say the first pass, you only wrote the code that does sampling, but you would like to compute the normalization constant. But you don't want to take care of all the accountings of creating this discretization of beta and communicating between chains in a distributed fashion and so on. So this is what this package does, so-called pigeons.jl. It will basically interface with your code in a very generic way and will compute the normalization constant in a scalable fashion for you. So the coding effort is very low, there's very low overhead, and this will give you distributed code that you can run on MPI, okay? And to reinforce this fact that it's low overhead, this is actually dimension independent. If there is a notion of dimensionality, like the message, the way this works is there's a process that manipulates several processes containing your MCMC code, And the way they communicate is just sending log likelihood evaluation. So the message is order 1. It doesn't depend on the state of the problem. And the communication by this fact can be very simple. It's this construct called the standard in, standard out, which every programming language support. And your code needs to accept message like, give me the value of the log potential at a beta, and please do some sampling at a prescribed temperature. And the Pigeon software will sort of orchestrate several of these processes and will output an estimate of Z-at for you. And for this project, we're really forced to work at the black box Lebesgue integral point of view. Now, this talk is a bit like, oh, this is possible. How can we do this nice little package? So there's an important part in kind of designing this meta algorithm, which is to choose which one. The literature is full of these algorithms actually that can deal with annealing sequence. And there's an important practical question, which is which of those should we pick? So I will start with a brief tour of these algorithms that work at the Lebesgue black box point of view. And they are broadly classified into those that are MCMC based and those that are particle based. So those that are MCMC based, at each step, they consider the anneal sequence and they move the iteration and go from left to right in that picture. So we have several particles living at different temperature. Particle-based algorithms are different, so you have several particles that each share the same temperature, and the time step is going up in that picture. So we go from by temperature, I mean that value beta that goes from prior to posterior. So in a slightly more detail, so for particle-based annealing algorithms, so the big families are anneal and importance sampling that was introduced by Neil in 2001, and annealed sequential Monte Carlo that adds a resampling step between some of these explorer steps. And this was introduced by Delmoral et al. In 2006. And I will use some terminology to distinguish how often this communication happens between the different particles. So if it happens at every iteration, we're going to call that continual resampling. And if it doesn't, then we're going to call it adaptive if it's sometimes there's resampling, and if there's never resampling, annealed SMC reduced to annealed importance sampling. Okay, so this is, because I talk about so many algorithms, I won't have time to review them in detail, but we will not, I'll try to abstract away some of the details of these algorithms. On the MCMC side, some of the classic players are parallel tempering and simulated tempering. With parallel tempering, I keep at each time step a copy at each temperature. And it gives us a nice trick where we can actually ignore we do not have to estimate the normalization constant to efficiently run that algorithm. With simulated tempering, we have only one copy moving in the state space. And for this to work well, we need some sort of rough estimate of this normalization constant. But the side effect is that we do have a regenerative structure that allows us to say more on central limit theorem and things like that based on this algorithm. Okay, so this is a very quick review of the classic landscape. And these algorithms, they were first studied in a reversible context, and later non-reversible version were studied and shown to perform better in certain circumstances. So again, so here I do my little stop, I do my Lebesgue compatibility check. And here I'm not going to have time to show it in detail, but the key point is that all these methods, PT, ST, SMC, AIS, the target in all of those, the target is manipulated through the log likelihood and the kernel, the explorer, K beta that target each of these. And I do not need to know more. So these are the sufficient statistics. The sufficient statistics is the energy in some physics terminology. So this means I can study these these algorithms both in specific case, but also in general case. So this is what we're going to do here. And we're going to talk about these interesting questions. So which algorithm to choose in a given context? Should we pick AIS? Should we pick SMC, PT, ST, or something else? And in order to answer this, we need to compare optimally tuned algorithm to optimally tuned algorithms. So we need to talk also how to do the tuning. So how to pick the number of particles, the number of iterations. In the PT context, it becomes the number of chains and the number of iteration, and also the schedule, beta 1 up to beta t. And all these questions, you can say something in the generic setup. Okay, it's not the perfect, but it's some generic recommendation. When we started this project, we sort of expected that maybe the answer would be model dependent, but it turned out the answer is more dependent on the computing architecture that you're going to use to deploy these algorithms. And so this is connected with this interesting question of how to leverage modern computing architecture, such as distributed computing, so MPI, and graphical processing units. And so the recommendation at the end will not be one thing, will not be like pick this algorithm. It will be basically some decision tree that depends on the computation time, the memory limit, and the distributed communication cost. And in some sense, even the economic model, as we'll see, do you get distributed computing in a package, or do you pay more each time you add a core? So we have two lines of work that are sort of moving towards like a more general theory. It's still fragments, but there's some interesting bits in there. So I want to highlight a paper by Biron, Campbell, and myself on parallel tempering and simulated tempering. So this is Miguel, who's now a postdoc at SFU. Unfortunately, I won't have time to talk too much about this. I thought I could cover more, but I invite you to look at the paper for more detail on the PT versus ST side of the story. And today I will only have time to talk about PT versus SMC versus AIS, which is joint work with Saf Said, who's just joined UBC, my former student, and my former student, Kevin Chern, who's at D-Wave, and my friend and collaborator, Arnaud Doucet. And so this part of the talk, we're gonna, in order to make this recommendation, we want to make this recommendation sort of in more general terms, so in terms of the complexity scaling rather than for a specific problem. So the setup is the following for complexity scaling and analysis. We seek to approximate Z to a fixed accuracy. So that's kind of the problem we're given. The asymptotics is interesting. We're going to have to imagine a sequence of integration problem, of Lebesgue integration problem that are getting more and more complex. So that's always how we do complexity scaling. If you study sorting algorithm, you look at problems that are bigger and bigger. So we need to do that here. So this will be interesting how we define this. We're going to need to define what we need. So the question is, how do we need to increase the effort? So we're going to need to define what we mean by effort. And we're going to do that as a function of problem complexity. So this is the main question. How do we need to increase the effort as a function of problem complexity? Now, in the next few slides, I'm going to define these bold terms in more detail. Then I'm going to talk about some simplifying assumptions that allow us to talk about this in a generic setup. And at the end, I will state the results. So let's talk about the bold term. So first, we need the notion of accuracy. So this is the slide that I'm just dissecting. So we're going to denote the normalization estimator by Z hat. What we want to minimize, a lot of people will agree, is the mean square of Z hat. The methods that we use, that we study here today, are unbiased for Z hat. And so equivalently, we can minimize the relative variance of Z hat for this discussion here. So this is accuracy. So Z hat to a relative factor. Now let's talk about the notion of effort. This is more complex. So there's many dimensions. There's the number of core N. There's the running time T. And there's actually more. So there's also the communication between cores, which is in the SMC setup, the resampling effort R. and also the memory consumption, which I'm not going to have time to talk about, but you can see the paper. And finally, let's talk about the notion of complexity. So the task here is to characterize the complexity of Lebesgue integral approximation. Okay? One of the classical approach for doing this is the dimensional TD. Unfortunately, that doesn't apply to that black box Lebesgue setup because there's maybe not a notion of dimensional T. So one innovation there is a notion of global barrier, which is this positive number that I'm going to denote by lambda, which in some sense, under simplifying assumption, encodes the intrinsic hardness of particle approximations of Z. Okay, so this is our notion of complexity. So I'm going to expand on that a little bit. So roughly to give you a preview of the results coming up, the relative variance of Z hat will be expressed asymptotically as a ratio where on the top we have the square of that notion of complexity lambda, the global barrier, divided by T divided by N. So we're going to look at a bit more detail on like the separate asymptotics of T and N, but this is for large T and N, that's a rough overview of our result. Now this global barrier is computed in terms of a local barrier, an integral from beta equals 0 to 1 of a function called the local barrier that encodes roughly how hard is it to move particles from beta to beta plus epsilon. Okay, so this depends on the details of the algorithm. If you use standard, in general term, this is the formula. So it will be the standard deviation of sort of a renormalized version of the weight update used in AIS and SMC. Okay, that we take the derivative with respect to beta prime. So now this general formula can be simplified in different simpler form. So for example, if you use what I would call maybe classical AIS, what a lot of people used for a long time was to use these explorer to be invariant with respect to beta and the backward kernel to be the time reversal. And in this case, we get this classical formula, the lambda being the standard deviation of the log likelihood when we compose it with the point x beta distributed at pi beta. Okay, and if you look at more trendy AIS that kind of use different things for the explorer, for example, an uncorrected deterministic flow, then you'll get a different special case of this formula here that depends on the characteristic of that flow. So just to give you a bit of visualization, so that these barriers, they can be estimated from the AIS SMC output, even if we view it from a black box point of view. We only need the weights, which are always defined for any Lebesgue integral. And so these barriers, we can always plot them for even phylogenetic problems. They look like this. So they're interesting. They don't always, the most effort is not necessarily close to the prior. Sometimes there are phase transition in between. And so it's useful to estimate them adaptively for building better grids. So I'm not going to talk about that today, but that's an important part of the methodology to build adaptive grid that spend more time on these parts of the continuum that are harder to approximate. All right, so I've finished that first part of like just describing that slide. So that was a bit of a detour, but there was some interesting bits on the way. Now I'm going to talk about simplifying assumptions, so a model for these meta algorithms that apply in the Lebesgue integration setup. Okay, and finally I'll be able to state one result. Okay, so this is this general question of how do we analyze meta algorithms. So what we're seeking is conditions where we think the meta algorithms can be efficient without making structural assumption on script x, the x-axis of my integral. And the idea here again is to loop back to Lebesgue a little bit and to look at the only thing that's available, which is the y-axis. So we're going to look at the sequence y1, y2, where yi is the composition of a point in an abstract state space with this log density. Okay. And just to give you a preview, a lot of these barriers can be computed from this, at least the classical ones. So this connects the theory nicely with the setup that I've described earlier. But so what we're going to do in a sense is a model. So we're used to doing model for data, and we know that these models are wrong, but sometimes they're useful. Now we're going to do it for algorithms. So we're going to build a model for the algorithms, for these meta algorithms. We know they're wrong, but based on empirical observation, they seem to be useful in some cases at least. And so this is an example here in the Ising model, where if I look at composition of some statistic, I can find statistics where the mixing is poor. Okay, so the magnetization, for example, is badly mixing for a naive Gibbs sampling. But interestingly, we found many cases like this where this specific statistic, the log density, is doing a reasonable job at approximating the distribution, even though some other test functions are mixing poorly. And so this is the motivation for the simplifying assumption called the ELE model. So where these yi's are modeled as IID. So there's a long tradition of doing that dates back from Radford-Neal. And clearly, there are algorithms outside of these regimes. You know, there's the Sharpie complete problem that will never approximate, but the key point is that often empirically, when meta algorithms work well, it seems that empirically the ELE is approximately valid. Okay. Some intuition why this may be the case. Of course, if the problem is well behaved, computing normalization constant is still interesting. So even for log concave problem, like the Lebesgue integration setup is still interesting because normalization constants are interesting and difficult. But there is also the case of difficult target where these annealing can also shine quite a bit. And one example that I prefer is the case of weak identifications where you have too many parameters. So the posterior distribution concentrate on a submanifold. And these explorer that I mentioned earlier, the local explorer, they can move it up and down that ridge a little bit, but they cannot go from A to B. So they can visit the altitude distribution, that sort of yi statistic, but they still cannot move globally. So in this case, if the curvature of that manifold doesn't change too much, the ELE could actually be a very close model of what's going on in the real algorithm. And essentially, the question of how to jump is what these meta algorithms answer. So they give you a way to exploit this local behavior into a global behavior by going through this distribution pi naught that we assume we can sample IID from. Okay. So finally, I gave a bit of an overview of the key technical assumption. I described what's the theoretical setup. Now I'm going to state the result. So that's the one way I like to describe this result is a cartography of particle annealers. And so what we're going to do, as I promised, is imagine a sequence of problems that are getting harder and harder. So remember, that means we'll let lambda go to infinity, the global barrier. And we need to think about how we're going to scale our efforts. Okay, but the problem is that these efforts are multidimensional. So we have the compute time and often we communicate. And so I'm going to denote each point in this graph as essentially a strategy of how I'm going to grow effort as a function of complexity. Okay, so I'm going to say that T is going to be the communication barrier it's going to be a polynomial, so to the power alpha sub T. So the larger alpha, the longer I run the algorithm as a response for harder problems. For resampling or communication, I'm going to use alpha sub R as the exponent. So the closer I am to this diagonal here, the more often I communicate. I cannot go above because just of the construction of how AIS or SMC is designed. So yeah, each point, the x-axis and y-axis gives me a strategy of how fast I grow time and resampling effort. Okay. Now, under simplifying assumption, the key one being the effective local exploration, the ELE that I described earlier, we have sort of like a partitioning of that space of strategies where if you give me these pair of points, so time and communication, Essentially, this theorem tells you, under simplifying assumption, how many particles do you need to get to a relative variance within epsilon of the truth, okay? So this is, in a sense, giving you what is the parallel cost that's needed if you want to fully parallelize these algorithms. And there's this sharp transition that the strategy, if they just cross these lines, there's a sharp transition in terms of the number of particles needed. And so if the schedule is very, very dense, then actually AIS or SMC with a single particle will be enough, because these distributions are so close together that a single particle, the discretization over the time step will give you a good estimate of the normalization constant. Now there's another extreme where if you're in a regime where the distributions are beta 2 are too far from each other, in this case you do need an exponential number of particles to basically get to this accuracy. And there's this Goldilocks region in between where you only need a polynomial number of particles, but where a single particle would, or constant less than that, would not be enough. So this is the stable regime. All right. So you can find existing algorithms in that picture. So for example, if you do AIS, there's no resampling, so you hug that line here. So there's never communication, and you look at different time scaling, and you see that you need roughly a scaling that's quadratic in that barrier to get a stable particle estimate. If you do adaptive resampling, you will naturally hug this boundary here. And so one highlight of this is the fastest stable particle algorithms, which is SMC, that maybe does not resample at every step, but up to a factor, linear factor does, which is what happened with adaptive methods. And that will take, in this case, order lambda time and order lambda communication, as well as order lambda particles. Okay, so this is kind of one sweet spot. But if for some reason you're a computer architecture where communication is really as a constant that's very expensive compared to the other constant, it might be interesting to consider this stable algorithm with the least communication in memory, which takes more time, but is to get to that point, but has no communication. All right. So this is how to interpret this result. So this was with particle methods. I want to talk at least a little bit about parallel tempering. So let me do that briefly here. So far, all this discussion was how to choose. I'll give you soon like a recap of how to, as a practitioner, how to synthesize all this. But let's talk briefly about parallel tempering. So recall that it's an MCMC method where now the chains, the parallel chains, are on this axis. They have different temperatures, and the iteration, so I'm going to call that n prime, and t prime is going to be the iteration on this axis. So it's the time homogeneous MCMC algorithm. What's interesting with the structure of that meta algorithm is that you can combine it with a stepping stone estimator, which when you write the estimator, so because the stepping stone estimator just needs an array of particles, basically of the format that PT or AIS gives you, and it has the same functional form as the Z-hat estimator of SMC. All right, and so if we flip the role of parallelism and time, so n prime becomes t and t prime become n, these equations, they look the same. So the dependencies how these particles are created is different, but in this meta algorithm context, they are not that different in the sense. So this gives us one way to talk about these two very different algorithms, PT and SMC, and put them neck to neck in this model setup. Now there is one complication to this argument, which is that PT algorithms are often not optimized for the variance of Z-hat. Instead, there's a parallel tempering specific criterion that comes from the physics literature called the round-trip rate. Now, what's interesting with the round-trip rate is that it yields a theory that's similar, but based on a different local barrier. instead of having the standard deviation of the energy, we have this expectation of absolute value of difference of two independent particles, their log likelihood at these beta. Okay, and so this ends up being the limiting, the intensity of a limiting PDMP that plays a special role in that round trip rate. So you see there's a gap here. So the theory of normalization constant tells you should optimize with this barrier, but the theory of round trip tells you should use this other barrier. And so there was this question, does lambda not equal to lambda PT? Does that make parallel tempering suboptimal for the purpose of normalization constant estimator? Okay. And the answer here was no, roughly. So there's exception, I'm sure, but in that sort of rough model, what we have is that the round trip, when it's well-tuned of PT, is asymptotically equivalent to optimal SMC for normalization estimation. Okay, so the round trip theory in PT tells you that n prime should be roughly in the order of lambda, and often lambda is often roughly 2 times the barrier. So the barrier from AIS is roughly 2 times the barrier from the PT barrier theory. So this observation is supported empirically. So you see, like, these are the lambda from the 2 different divergence that are estimated for different problems. But also there's some theoretical justification that if you're in the special case that your target is a product space, which is an even cruder model, but in that regime, then the lambda from AIS or SMC will be roughly square root of pi, pi 3.14 times lambda PT. Okay, so they are indeed related. And so the end product of this is that running PT for t equals to order lambda can match the fastest stable SMC algorithm. Okay, so this is interesting. So just to give a bit like a more practitioner-friendly way of summarizing these results, which algorithm should you choose? So as I said, this depends more on the compute architecture that you're going to deal with. So if you're using your laptop, so you have serial computation or very limited parallelism, optimally tuned SMC, PT, and AIS will perform similarly. So we've tested that empirically as well, and that seems to be true in many problems. Now let's talk about parallelism, and here I'll put a little economic model that distinguishes 2 cases. The first is in bulk, by which I mean each time you add 1 more core, you pay a little bit more, either in money if you're doing AWS, or if you're in a HPC setup, your queue time decrease. So if you're in that regime, then go with SMC or PT. There's a little disclaimer with PT, which is in the high parallel regime, at some point with PT, what you need to do is to not make the schedule denser, but to have parallel copies of parallel tempering running. So that's what we call sometimes parallel tempering. So with that disclaimer, then SMC or PT are interchangeable. If you're in the package, what I call the package parallelisms, which means that on your laptop, there's 10,000 core. You might as well use them all, right? Whether you use 100 or you're not, the marginal cost is very small. There's electricity, but yeah. In this case, it might actually be useful to try AIS. And so I put a skull in that zone here. But actually, if you're not paying for your GPU, it might actually be worth venturing a bit in that zone here, because the communication cost is so high, you really want to stay in the AIS regime, and you need an exponential number of particles. But for some problem, 10,000 is close to an exponential cost, roughly speaking. So that's why I wrote this thing, that in some cases it could be useful to try AIS in the GPU setup. And we've done some experiment, and that seems to be very effective indeed. If you're in a memory constrained environment, so I haven't talked about that, but for some combinatorial problems, each copy of X takes a lot of memories. And AIS has this interesting property that it actually has a lower, the lowest asymptotic memory requirement. So you can look at the paper. So there's this interesting twist here that you have. So just briefly, I'm almost out of time, so just a few minutes for pointers and software to use these methods. So I mentioned briefly at the beginning pigeons. So it's we're working on this easy-to-use software for Lebesgue integration. So I emphasize it can work with several APIs. So one of them is this very generic API where you communicate with external processes. That could be MCMC running in any language. But there's also some nicer interface if your model is in Stan or Turing or Blang, then there's some simpler way to use it as well, where the sequence of distribution can be built automatically for you, for example. I think one highlight of this package is that from the very beginning, we built it with the distributed computing setup in mind. So we've tested it with over 1,000 processes, CPU processes, and we tried to make it easy to use. So if you're, for example, using Compute Canada, you can use a one-liner to set up for your cluster. And then by using the same syntax, but adding sort of like a prescription that you want to run this job on MPI, it will automatically manage the submission to the queue and collecting the result and things like that are common friction point for distributed computing. And this is possible thanks to this fact that the sufficient statistics are very light. It's just the log density evaluation that are shared. And even if no matter what number of processes that you use, for a given random seed, you'll get exactly the same output. So there's this very strong reproducibility that no matter how many processes you use, you get exactly the same result. That was carefully baked in. So I think, yeah, this setup of computational Lebesgue integration, I think, is rich. There's surprisingly rich. It looks very bare bone, but there's actually some things to do. I give here pointers to, there are many papers. People have been working on this field since the 90s at least. But yet there's still interesting methodological question. So I talked a bit about which meta algorithm to use, but there's still an important thing about tuning that I haven't mentioned. And there's also this interesting question, whether there are new useful meta algorithms that are not yet discovered. So all of these, they kind of like, several of them seem to work similarly, but we see with different computational regime that there starts to be interesting differences. And now that computing architecture are evolving quickly, I think there might be new meta algorithms that emerge and that haven't been used before. There's a lot of interesting theoretical questions. So we usually take asymptotic where D goes to infinity or N goes to infinity. But yeah, I've discussed some alternative where you look at some sequence of divergence value that go to infinity that apply in a more generic setup. And so I want to highlight this recent paper with Nicolas Surjanovic on geometric ergodicity of PT under that algorithmic model, which is, again, surprisingly rich. This was a very hard but rewarding project to work on. And also, I'm generally interested in benchmarking these methods on genuinely hard problems. So if there are applied statisticians that work on challenging Lebesgue integration problem that feel all current algorithms are failing them, I would be really interested to hear from them and to try to push the boundaries. And at some point, we'd like to submit a joint resource paper that share some of these hard Lebesgue integration problems that no current method are able to tackle. And so I would like to thank again my amazing collaborators. If you're interested in this, you can access the software, the open source software at this address. The documentation is there, and the bibliography is at this link. And thanks again, the organizer, for this wonderful series.